And here we are on problem 57 of electric circuits. This is our last example problem from the circuit section, and then we will move on to electromagnetic waves, which is the final section in the book. So we are going to consider the circuit at right, which has two resistors and an inductor. We want to know what the current through R1 is and what the current through R2 is immediately after the switch is first closed. Well, remember from the induction section that nature abhors a change in flux. And so, before the switch is closed, the current going through the inductor is 0, of course, because the switch is open. And immediately after the switch is closed, nature is abhorring the change in flux, and the current through the inductor immediately after the switch is closed is going to be the same as the current that was going through the inductor immediately before the switch is closed. So there's no current going through the inductor at this moment in time. Therefore, the current that's going through resistor 1 is the same as the current that's going through resistor 2 because the inductor at this moment is acting like an open switch, so there's no current going through this branch. So the current going through R1 is the same as current going through R2, so I'm going to say IR1 is equal to IR2, and let's say IL is equal to 0. So we just have to figure out what that current is. Well, my favorite way of doing this is to find the effective resistance. So you can pretend the inductor's not there. So we have two resistors in series. So the effective resistance for two resistors in series is just equal to R1 plus R2. I want to know what the current is. Well, the potential for the battery is V, and then I can just use Ohm's law and say V is equal to I times R, where V is V. I is the current that I'm looking for. That's the current through R1 and also the current through R2, because they're equal. And the effective resistance is R1 plus R2. Therefore, I is equal to V divided by R1 plus R2. Again, that's not the only way of solving the problem, so if you would like to solve it a different way, as long as you get the same answer, well, it should be all okay. What is the current going through R1 and the current through R2 long after the switch is closed? After a long time, long after the switch is closed, delta VL is equal to 0, which I think we just saw in a previous problem. So hold on just a minute. So we can see that from the equation that they give us here. Can we? No, we want to look at the equation that's here because we're looking at the potential. So long after the switch is closed, the potential across the inductor is equal to negative V times e to the negative t times r divided by L. Long after the switch is closed, if you say t is equal to infinity, you have e to the negative infinity, which is going to 0. So we have this from that equation. So, if the inductor is just like a closed switch, long after this switch is closed, then what we have for our circuit long after the switch is closed looks like this. Okay, so it's like the inductor is just a closed switch. So then, why would the current want to go through this branch where there's resistance when it could just go through this branch instead? So we're going to have no current flowing through this resistor because there's a path with no resistance over here. So the current going through R2 is equal to 0. And if no current's flowing through here, then it's just like a circuit with a battery and one resistor. So that's pretty easy. You would say V is equal to IR. R is just R1, so IR1 is equal to V divided by R1, and that's it. Maybe up here I should have said IR1 is equal to I, R2 is equal to I. Okay, and then I want to know what is the current through R1 and the current through R2 immediately after the switch is opened after being closed a long time. Okay, I'm going to redraw this. If the switch is open, then no current can flow through this branch, so it's just like the inductor and resistor 2. So we can ignore everything else because the switch is open. So we have our inductor here, and we have resistor 2 here. Now, as we said up here, nature abhors a change in flux, and so the current that's going through the inductor immediately after the switch is opened is the same as the current that was going through the inductor right before the switch was open. So that's like the opposite of what we said up here because the switch is being closed. But immediately before is the same as immediately after for the current going through the inductor. So I need to know what current was going through the inductor immediately before. Well, that comes from what I have up here. This is the current going through resistor 1 long after the switch is closed. So we opened up the switch after it was closed for a very, very long time. So the current in this case is equal to V divided by R1. Now that must also be the current that's going through this resistor, because if that's going through the inductor, it has to go through resistor 2. The only thing that you might want to indicate in your answer is that now the current's going this way through the resistor. I called this IR1. That was actually bad because here, after the switch is open, the current that's going through resistor 1 is equal to 0. So that's one answer. This was the current that's going through resistor 1, but now it's the current that's going through the inductor and resistor 2. And I guess if you wanted to put a negative sign in there to show that it's going in the opposite direction of what it was up here, you could do that. I probably wouldn't care about it if it was homework, but maybe draw a picture so we know what's going on. So that concludes problem 57. I like problem 58. It's very similar to problem 57, but instead of asking about the current, they're asking about the potential. So I think that actually what you could do for problem 58 is just take the current that we have here, and using Ohm's law, if you want to find the potential, you would just have to multiply by the correct resistance. So that seems to work there. Yes, you multiply by R1 and R2, and that gives you the potential. And then here, multiplying by R1, that would give you V. This would be 0. So that gives us what we have here. And then I1, what does this see? R1 will be removed from the circuit. Therefore, V1 is equal to 0. Very good. Okay, so that agrees with what we said here. And then you would just take this and you would multiply it. Since it's resistor 2, you would take this and multiply it by resistor 2, which is just what they have here. Okay, so you can read through the solution that they give you for problem 58, but basically you can find the answers just by taking what we have for 57 and multiplying by the appropriate resistance. The reason that I mention that is because problem 59 and problem 60 are homework problems, and they're similar to 57 and 58 in that it's the same diagram, and one question's asking about the current and one's asking about the resistance, but we will talk about that in the next video.